Marco Colussi from Vicenza, and the work I'm going to present deals with the investigation of the fracture behavior of cracked giant magnetostrictive materials. The condition that had been considered was 3-point bending and the effect of the presence and the absence of the magnetic field and the effect of different loading weights had been considered. The final goal was to try to establish whether the average strain energy density criterion is suitable for predicting magnetostrictive materials' failure. A brief introduction on the studied material. Magnetostrictive materials are part of the category of smart materials, which are materials that change one or more properties as a consequence of an external force field. In the case of magnetostrictive materials, the external force field involved is magnetic and the modification is geometrical. So because the internal domains of the material are elliptical and they rotate and stretch in the presence of a magnetic field, as a consequence, an elongation or restriction is produced. These materials find many applications in automotive industry, in avionics, and in robotics, both as sensors and actuators. Among giant magnetostrictive materials, we consider the commercially named terphenol T, which is provided by a tremor. This material is an alloy of iron and rare earth, terbium and dysprosium. We choose to study this material because it is one of the most commonly adopted in the applications, and this is because it has an extremely short reaction time, and a high saturation level, and a high Young model. Despite this material is really brittle. And once again, this is a motivation for the study. In our previous study, we considered the same material and presented a set of 12 specimens made out of terphenol T, loaded under 3-point bending. And in that occasion, the energy release rate criterion was considered. It had been found that terphenol T show a decrease in the fracture load in the presence of a magnetic field. And this behavior was justified by the increase of the energy release rate with increasing magnetic field, as it's possible to see in this plot. In the present study, we present a new data set of specimens tested under mode 1 loading condition, 3-point bending. Testing apparatus and the specimen are here presented, and a uniform magnetic field with induction 0.03 Tesla was applied in the longitudinal direction. Also, different loading rates were considered, respectively 0.03, 0.5, and 3 Newton per second. Moreover, the set strain energy density criterion was considered instead of the energy release rate criterion. Specimens were cracked with a crack every length 0.5 millimeters. Here are presented test results in terms of average fracture load. It has been found that in the presence of the magnetic field, we have a reduction in the resistance. This reduction was about 13%, 9%, and 7% by reducing the loading rate from 3 to 0.0305 Newton over second. Moreover, it has been found a reduction in the resistance, a further reduction in the resistance, reducing the loading rate from 3 to 0.5 Newton over second. While a good agreement was found by reducing furthermore the loading rate. Next, I talk about the analysis. Here are outlined the constitutive equations of the material. So we can see an orthotropic material, and also we can see the material dependence, the stress dependence on the magnetic field. Moreover, being the magnetostriction of this material no linear dependent on the magnetic field, we introduced also a second-order magnetoelastic constant in the longitudinal direction. two-dimensional finite element models were considered and the assumption of plane stress was made. This is because specimens were really thin, only 3 millimeters. And then because the basic equation of magnetostrictive materials are formally equivalent to those of piezoelectric materials, we considered coupled field analysis, piezomagnetic, and the magnetic field was introduced by a voltage difference. According to the average strain energy density criterion as formalized by Lazzarini, greater failure occurs when the strain energy density averaged in a specific control volume that in the case of cracks is circular and centered at the crack tip reaches a critical value. This critical value can be computed according to Vitami with this formula, and introducing in this formula the average value of the tensile stress and the Young module provided by the material supplier, we can find this critical energy, 0.02 megajoule over cubic meter. Then, by computing with the finite element models the strain energy density, and by plotting this energy in function of the radius of the control volume in the presence and without the magnetic field at the corresponding critical measured load, it is possible to find an intersection. This means that at the critical condition, the material is characterized by an energy average in this control volume, which is dependent on the ratio between the magnetic field and the external load. Then, one fixed the control volume dimension, it is possible to compute and plot the energy versus external load. And also in this case, we can see that in the presence of a magnetic field, the energy is always higher. And this justifies the fact that specimens face at a lower level in the presence of a non-zero magnetic field. Then, repeating this procedure for each loading rate, it is possible to find different intersections. A good agreement of the trend of this intersection versus the loading rate to a linear model has been found, and so this simple linear relationship is proposed. Finally, using this relationship, it has been possible to summarize all experimental data into a narrow scatter band ranging from 0.8 to 1.2 in terms of the square root of the computed energy over the critical energy. And we think that this could be a good result for an engineer which needs a criterion to establish the fracture of this material. In conclusion, under mode 1 loading condition, definitely shows a decrease in fracture load in the presence of a magnetic field. The fracture load is affected by the loading rate, and the self-criterion seems to be able to capture this behavior. Points that remain open are mixed mode and the extension to other materials. We are now working on both points, and we are studying another material named galphenol, which is a gallium and iron alloy, and with reference to mixed mode, we just finished a few days ago test, and but we had not time to perform the analysis, so I can only give you a review. We considered this condition of testing and considered different value of the distance between the crack line and the loading point. So when t is equal to 0, we have a mode 1 loading condition, and the other condition are mixed mode. Also in this case, we can see a reduction in the resistance in the presence of a magnetic field. Thank you.
Thank you.